So in this second part of the video, we're going to look at a little bit of background on modular arithmetic, how RSA works. Then we go back to RSA, look at its vulnerabilities, look at how to improve from vanilla RSA to real RSA, and then some other public key encryption schemes, and then conclude the part on public key encryption scheme. So let's go to the board for some modular arithmetic. So as I was saying before in the video, modular arithmetic, you should be all familiar with it. For instance, when you compute with the clock, know that if it's 10 a.m. and we say we're going to meet in 3 hours, well, that's 13, but we're really doing computation modulo 12, which means that this is equal to 1. So we say that 13 and 1 are equal, 13 modulo 12 is equal to 1. How did we get this to this number? We got to it by saying that 13 is equal to 1 times 12 plus 1. So this is the remainder. This is the part we're interested in, which is the one that is popping up here. So often we also say that 13 and 1 are congruent modulo 12. And when we do long computation with modular arithmetic, we usually just write the modulo once, because otherwise it's just boring. Another interesting thing to know about modular arithmetic is that you can do a lot of the regular operation you're used to. So, I mean, if you have that 13 is congruent to 1 modulo 12, you can add something on both sides. You can add 2 here, you can add 2 here, and these 2 things will still be equal modulo 12, as you are used to. And you can also do multiplication on both sides. So, I mean, if 13 is equal to 1 modulo 2, then it's also true that 3 times 13 is equal to 3 times 1 modulo 12. And those are easy things that you can check on yourself. For instance, 3 times 13, 39. Well, 39 modulo 12, let's write it down. 39 is equal to 3 times 12 plus 3. And this is the 3 we're interested in, which is the same as that one. But that's great. Something which is slightly less immediate to do in modular arithmetic is to do inversion. So what is division in modular arithmetic? So for instance, I could ask you, what is 3 inverse modulo 7? So let's call this value x. So this is not an integer division. This is not 1 divided by 3. X here is the number such that if you take x and you multiply it by 3, you get 1 modulo 7. So in this case, this is easy to compute. Just by simple intuition, it looks like 5 times 3 is equal to 15, which is in turns equal to 1 modulo 7, because 15 is equal to 2 times 7 plus 1, and this is the value we're interested in. So it was quite easy to do this inversion in my head. More in general, if you want to do inversion with modular arithmetic, there are algorithms that do that for you, and your programming language probably has some library for doing modular inversion. The most important thing here to remember is that if you implement some of these yourself, you should not divide. This is not 1 divided by 3. This is not 1 divided by 3 in the usual sense. Something else which is nice to know about modular arithmetic is that it's very easy to compute powers, large powers modulo in modular arithmetic. And this is going to be very, very useful when we do RSA. For instance, we could do an example which is to compute 3 to the 129 modulo, I don't know, say modulo 7 to do an easy computation. So how would you do this computation? So if you start by first computing this 3 to the 129, 229, and then you do the modular reduction, well, that's simply not going to work. This number is so big that your computer is not going to be able to store it in its memory. So you can't compute 3 to the 129. And this is even a small example. When you're going to do RSA computation, you're going to have to deal with even larger numbers than this. So how can we do this? So the trick here is to remember that modular reduction can be done at any stage of the computation. So in particular, if you have x squared modulo 7, this is equal to x modulo 7 times x modulo 7 all modulo 7. So what can we use this for? We can use this for doing this computation in a much easier way. So what I'm going to do is that I'm going to take this computation and I'm going to do it in small steps. So first of all, I'm going to notice that 129, which I've chosen on purpose, it's equal to 128 plus 1. So this is going to be very useful here. So I can start with 3, and I can ask myself, what is 3 squared modulo 7? Well, I have to do this. There is no other way than doing this plainly. So that's going to be 9, which is equal to 2 modulo 7. Great. And now I can ask myself, what is 3 to the 4th modulo 7? Well, I could, of course, compute this directly. It's not such a big number, so I could do it. But I'm lazy. So instead, I'm going to remember that this is equal to, since I already know what 3 to the second is, I'm going to write this as 3 to the second modulo 7. But since I already know what this is 2. This is 2 to the 2 modulo 7, which is equal to 4, which is a much smaller number to deal than the others. So in fact, now I can just write then that I have that 3 squared is equal to 2 mod 7. 3 to the 4 is equal to 4 mod 7. And now I can ask, what is 3 to the 8? 4 squared, that's 16. Well, that's equal to 2 modulo 7. Oh, in this case, I was kind of lucky. So this is simply going to keep swapping between 2 and 4, 2 and 4. And eventually, I can compute what is 3 to the 128, which is a power of 2. And then I can take this one, multiply it by 3, and find out what this is modulo 7. And you can see that I didn't have to compute this huge number. I just had to compute all these small intermediate values. And of course, there are many fewer of these. So this is a very nice trick to do big exponentiation module when you deal with modular arithmetic. So let's see a few more things about RSA. So let me remind you that in RSA, N, the public key is the product of 2 large primes, P times Q. And I told you that E is chosen as a, well, those are primes, large primes. So E is chosen as a small number, like it's going to be something like 3 or some 2 to the k plus 1. Typically a small-ish number. And then D, I told you before that it was computed as a function of P, Q, and E. Let's see exactly which function it is. So D is going to be the inverse of E modulo P minus 1 times Q minus 1. And the reason why we use P minus 1 and Q minus 1 is due to the algebraic structure of arithmetic modulo N, where N is the product of 2 primes. So D is equal to the inverse of E, meaning that D is going to be the number such that if you take D times E, you get 1 modulo P minus 1 times Q minus 1. So this is not the inverse in the usual integer sense. This is that number that if you multiply with D, you get 1 modulo P minus 1 and Q minus 1. And since these prime numbers are going to be very large, thousands of bits, as we discussed before, doing this inversion will not be possible to do this inversion in your head like we did before. You're going to have to use some algorithms. And the algorithm that does this for you is the extended Euclidean algorithm. Right. So what else would I like to tell you? Okay, so for this inverse to exist, you need E to be coprime with P minus 1 and Q minus 1, meaning that E should not have any prime factor in common with P minus 1 and Q minus 1. And this immediately tells you why I started with 3 and not with 2. So P and Q are large prime numbers, so they're odd. So P minus 1 and Q minus 1 are even, so 2 divides both P minus 1 and Q minus 1. So E cannot be 2 or cannot be a multiple of 2. So that's why we choose some other value. It's not clear that 3 can be used always, right? I mean, if P minus 1 was divisible by 3, then you could not use 3. Right. So that's how D is computed. It's actually computed. So let's see how RSA encryption is done. We'll leave this fact here because it's going to be useful in a moment. So RSA encryption is done by taking the message, raising it to the E, and then computing modulo n. That gives you the ciphertext C. And then I told you that decryption is done as follows. You take the ciphertext, you raise it to the D, and then you compute modulo n. Let's check why this works. So I can substitute here that. So I get that this is equal to the message raised to the E modulo n, raised to the D modulo n. But I told you that the modulo n, it doesn't matter where you do them, so I can remove this one, so I don't have to remember all of the notation. So due to the power of exponentiation, this is equal to n to the E times D modulo n. But D and E have been chosen to be the inverse of each other, which means that this is equal to n raised to the 1 plus, what does it mean that D times E is equal to 1 modulo this value? It means that D times E is equal to some number, which is a multiple of P minus 1, Q minus 1 plus 1. So this is 1 plus some multiple, let's call it K, of P minus 1, Q minus 1. Now, because of the algebraic structure of arithmetic modulo n, anything raised to the P minus 1, Q minus 1 is equal to 1. So this is equal to m raised to the 1 times m raised to the P minus 1 times Q minus 1 all raised to the K. So this is 1, which means that the whole thing is simply equal to m modulo n. And this is why RSA works. So we tell you this for completeness, is not, some of you will not have the mathematical background to go through these steps, but it's nice to know, and you might want to know this in the future. So let's go back to the slides. So again, recap on vanilla RSA. Public key has these two values n and E, secret key these two values n and D. It's hard to go, it must be hard to go from n and E to n and D, which implies that factoring n must be hard. Encryption and decryption are computed by taking some number and computing an exponentiation. D is a huge number, so when you do this C to the D modulo n, you can't simply compute C to the D and then take modulo n. You have to do some kind of a smarter algorithm like the one I showed you before, where you take C squared, take modulo n, and so on. And then you work your way up to the D. And because the public key and the secret key are related, and you can always factor n, then P and Q need to be large, or at least larger than the length of the secret keys. In secret key cryptography is going to be like 2000 bits. So the title of this slide says that RSA encryption, or the vanilla version, is insecure. And why is that the case? Remember the definition of security. Remember the definition of security for public key encryption. We say a scheme is secure if the adversary cannot distinguish between encryption of messages that it chose from messages that from random messages. And we had this attack in which the adversary can always simply re-encrypt the message and check whether this is the case. And that's why we need randomness in public key encryption. So vanilla RSA doesn't have any randomness. There is no randomness involved. So it's clearly insecure. If I give an encryption of a message, you can always, and you have a guess at what the message is, you can always simply try to encrypt the message you think it's there, raise it to the E, compute the ciphertext, and then check if it's the same ciphertext. So in some sense, you can brute force the message, right? You can try all possible messages, encrypt them, and check if it's equal to the ciphertext. So there is a huge difference between brute forcing the message and brute forcing the key. So the key is large and chosen at random. So brute forcing the key, while it's inevitable, it's usually not a problem, because you can just choose the key to be large enough such that brute force will not will not be feasible in any meaningful amount of time. But if you can break something by brute forcing the message, well, that's a much bigger problem, because the message typically is not chosen at random. I mean, the message has some value. Maybe this is an encryption of a message that says yes or no. So there is only one bit of entropy. There are only two possibilities, and then I mean, you still want to be able to encrypt a value, a message which only has two possible values, yes or no, in a meaningful way. So that's why a scheme which doesn't have randomness cannot be secure. So the first problem of RSA is that it's doesn't have any randomness, and if you think about what happens if you even encrypt a bit, right? If your message is added 0 or 1, what happens when you encrypt it? So 0 to the e, what is 0 to the e modulo n, and what is 1 to the e modulo n? I like to say if an encryption scheme cannot be used to encrypt bits, then you shouldn't use to encrypt anything. So that means that we need to add some randomness to RSA to make it secure. Another problem that RSA has, or more in general, public key encryption scheme have, is that they're much slower than the secret key cryptography. So if you use AES or AES in CBC mode, you can encrypt a large amount of data in very short time. Whereas public key cryptography, since it requires to work with this modular arithmetic, it is much less efficient. It's fast, but not as fast. I mean, if you have to encrypt gigabytes of data using RSA, it will not be as fast as you want. So because of this reason, there is this standard trick known as hybrid encryption, which proceeds as follows. Instead of, let's say you want to encrypt a DVD, instead of encrypting the DVD using RSA, you pick a secret key for an encryption scheme like AES, and this is a short key, like 128 bits. And now you encrypt this key using RSA. And then you encrypt the DVD using this short key and using AES. So now this encryption is a bit slower, but it doesn't matter because you're only encrypting a short message. And this encryption is much faster, which is nice because you're encrypting a much longer message. So the encryption on the receiver side works as you would expect. So the receiver who knows the secret key for RSA decrypts RSA, the RSA ciphertext, and receives the key. And now with this key can decrypt the actual message which was encrypted using AES. So this gives this now gives you a problem. You need to find a way how to encrypt short keys securely using RSA. The third and final problem of vanilla RSA is that it's not secure against chosen ciphertext attack. So what is a chosen ciphertext attack? A chosen ciphertext attack is an attack in which the adversary has access to a decryption oracle. So let's see the definition of this. So a chosen ciphertext attack is an attack in which the adversary, for some reason, has access to a decryption oracle. So someone is decrypting ciphertext for the adversaries, and we still want the encryption scheme to be secure, even if the adversary can ask decryption of ciphertext that he likes. So this sounds a bit weird. Why would adversary have access to a decryption oracle? Why would someone decrypt messages for the adversary? And again, so first of all, this can happen in the real world. I mean, you can have a server that is running some service, which, as part of this service, it's decrypting some ciphertext and sending back some plain text to the sender. Maybe the server doesn't send back the exact message that it was received. Maybe it sends some function of the message. Imagine a database into which you can send an encrypted query, and then the database decrypts the query and then sends you back some answer. Maybe you're like, it's a Google search. You can send an encrypted Google search where you ask for something, and then the server returns you the result. So maybe you don't get exactly the decryption of the ciphertext you ask for, but maybe you get you maybe get a function of the plain text which was encrypted. still you learn some information about the plaintext. And since we are cryptographers and we're paranoid, if we ask security in the worst case scenario, if you ask security in the case where the adversary has access to an oracle that decrypts arbitrary ciphertext of his choice, then we automatically get security also against an adversary who has access to partial decryption oracles. So how do we model this? So here again, we have this definition of security, which is modeled with these two games, a real game and a random game. In the real game, the adversary gets the public key and then picks a message of his choice and then gets an encryption of that message. Notice here that I'm using the randomized notation, so this ciphertext is randomized. In the random case, the adversary chooses again a message, but instead of getting an encryption of that message, he gets an encryption of some random value. And then after the adversary gets this ciphertext, the adversary has the ability to ask the magic box to decrypt some ciphertext. So now, if the adversary could choose to decrypt exactly this ciphertext, the one we call the challenge ciphertext, then it would be trivial to break the security. I mean, you just ask the ciphertext again, you learn the message, and then you can distinguish whether this was the same message you asked for or something else. So we in the definition, we say that the adversary can ask for any other ciphertext which is not this particular ciphertext. And then the box will decrypt this ciphertext for the adversary and return the answer. So now we ask that the adversary can't tell whether this ciphertext is an encryption of M or some random garbage, even in the case where the adversary can get access to this decryption oracle. So this is pretty much the strongest possible definition of security you can imagine. So to deal with this kind of attacks, actually to deal with all of these problems above, so to deal with the problem that vanilla RSA is insecure, so you need to add some randomness. The fact that you need to be able to encrypt a short message into message which maybe is only 100 bits into a space which is like thousands of bits, and most importantly, that is not chosen ciphertext attack, or as importantly, I mean, the first problem is also really, really important. So OAEP is used. So OAEP is not described in the book, but I thought I would add it here on the slide so that if you're interested, at least you can look at this. So OAEP stands for optimal asymmetric encryption padding. So it's a padding scheme. It's a way of taking a message and of a fixed length and pad it to the size of the RSA modulo. So this is done using some randomness, which, as by now you now know, it's necessary to get security, any meaningful notion of security, even just chosen plaintext attack. So OAEP is an invertible function. So this is not an encryption scheme. It's an invertible function. It's very easy to invert, which maps a message. We take some message and some randomness, maps it into something, and then you can go back. So the way you use OAEP would be that you take OAEP, which is a function of the message. Then for technical reasons, you add a bunch of zeros and some random value that you choose for every encryption. Now you take the padded message, you raise it to the E, and that's your ciphertext. When you decrypt, you take the ciphertext, you raise it to the D, which is the standard RSA decryption, and then you get back the output of this OAEP. So you have to invert OAEP, which is again it's a function which is easy to invert. There is no key, there is no secret key here to invert the OAEP function. When you invert the OAEP function, you get the message. You get something here in between, and you get some randomness. Now in the decryption, you check whether this thing that you got here in the middle is a string of zeros. If it is, you conclude that the decryption was successful and you output the message. Otherwise, you say that the decryption was unsuccessful and you say and you abort. So the decryption aborts. So it's very important for chosen ciphertext security that that there is this condition that the decryption might abort and might say, this is not a valid ciphertext, I abort. Because this is what ensures that essentially the adversary can't just pick a random ciphertext, sending them to you and get them then decrypted. Because if it does that, with very high probability, the decryption will abort and will tell the adversary, this is just an invalid ciphertext, what are you talking about? So the fact that the decryption can abort essentially forces the adversary to only the adversary can only get decryption for ciphertext for which he knows what the plaintext is, which makes the decryption oracle essentially useless in the definition. What I'm saying now is not technically part of the curriculum, but I think it's interesting. So some of you might be interested in this. So let's see how OAEP works. So how can you have a function which maps a message, some zeros and some randomness into something, and it can also be inverted. So here's how OAEP works. You start with a message and this bunch of zeros, and that's a long string. And then you start with some short randomness here, R. So there are two functions, G and H. So G takes the randomness R and expands it into a long string. So R is turned, it doesn't matter how G and H work, but G is just going to map this randomness R into a longer string that can be XOR with M and the zeros. So you take the randomness, you expand it into a longer string, you XOR it with M, and that gives you U, the first part of the padded message. You also take this output of XORing the expanded randomness with the message, and you give it as input at H. H is a function that takes a long input and shrinks it down into a shorter input, a shorter output. Then you XOR this with R, and you call this V. So this is a very nice structure, which is invertible. And I think, maybe this is a good exercise for you if you want to think about why this is invertible. If you have U and V, how can you retrieve M, the zeros and R? So you have to think about going back, right? So you have U, you have to go back. How do you get this? Or to get this, need to get this value. So how do you get this? Or to get this, you need to get. So think about it. So this is a structure which is invertible and produces from M a bunch of zeros and R, produces some U and V. So what's important here is that you start with a message which might have been short, might contain some zeros, and what you get out here is as long as it's a number between 0 and n, and it's random looking. So G and H have the property that will produce some U and V here, which are random looking. And I don't need to say anything more for this part of the course. Okay, so just a few final notes, and you can read much more in the book about this, about other public key encryption schemes. So RSA is great, and it's the first public key encryption scheme we had, and for a long time has been the most used public key encryption scheme we had. But recently is being challenged and is being replaced by other public key encryption schemes. So one very popular public key encryption scheme is the El-Gamal crypto system. The El-Gamal crypto system is based on a different mathematical problem, so it's not based on factoring. It's based on something called discrete logarithms. We talk more about discrete logarithms in the chapter about network security. The reason why El-Gamal is becoming popular is because it's much more efficient than RSA when it's implemented over elliptic curve cryptography. So elliptic curves are some fancy algebraic object which allows you to define something which looks like modular arithmetic. You can have a group if you've taken algebra and you know this term. You can define a group over the point of an elliptic curve, which allows you to do some operation for encryption. And the nice thing about groups defined over elliptic curves is that the best attacks over elliptic curves are essentially brute forcing. So in RSA, since factoring is factoring is very hard, but it's much easier than brute force. In RSA, we had to use keys which were very long, like 2000 bits. Since elliptic curves are more secure, that you don't have these attacks, then it's if you want security equivalent to 2000 bits in RSA, in elliptic curve cryptography is enough to use keys which are like 256 bits. So having much shorter keys, it's a very good property for application in which bandwidth is essential. And that's why it's not surprising that Bitcoin, for instance, or any other blockchain project really uses elliptic curve cryptography because it's very, I mean, when you have to put public keys on the blockchain, it's very important how long these public keys are. So the shorter they are, the cheaper it is. So elliptic curve cryptography is winning there. A completely different story is that most computer scientists, most cryptographers are not talking about if a quantum computer will arrive, but when a quantum computer will be available. And you know, regardless of if or when a quantum computer will be available, then RSA and elliptic curve cryptography, for that matter, will be completely insecure. So quantum computers can factor and can break elliptic curve cryptography in polynomial time. So this means that if you want to build a system which has to be secure for the next 30 or maybe the next 50 years, then it might be a good idea. If you're afraid that quantum computers will become a reality in the next 30 to 50 years, then it might be a good idea to deploy post-quantum cryptography. So post-quantum cryptography is cryptography which is secure against quantum computers. So currently NIST, which is the National Institute of Standards and Technology in the US, who's the main body worldwide that standardized cryptography, is running a post-quantum cryptography competition. We are now at around 3 of this competition, in which, similar to what they've done before for symmetric encryption schemes or hash functions that we will talk about in other lectures, they've asked cryptographers from all over the planet to submit their design for encryption schemes which are believed to be secure against quantum computers, and then cryptographers are trying to break each other's schemes, and then at the end someone will win. We also had a submission from OAEP. I was part of a team which was led by some Microsoft researchers and then researchers from lots of other universities all over the world, including me, not for encryption scheme, from a signature scheme called Picnic, which is now been identified as a possible alternative scheme in round 3. So, which is nice. It means that it's no vulnerabilities have been found, but for efficiency reason, it's not going to be chosen as one of the primary options. So another thing which is very important to mention when we talk about post-quantum cryptography is that only classical public key schemes like RSA and Kamal or discrete logarithms are affected. Symmetric cryptography is essentially not affected by quantum computers. So if you've ever heard anyone saying that quantum computer can solve everything, that's not true. Quantum computers can only solve certain classes of problems in polynomial time, but there are still things that we believe are hard, even for quantum computers. So for instance, if you want security, if you want a secure symmetric encryption scheme, which is secure against quantum computers, essentially you can just use AES with a slightly longer key.